Today we're going to talk about part 3 of chapter 2 about resistive circuits. The modular objectives are as follows. The first one is circuit analysis using resistor combinations. The second topic is relatively new, so that is delta Y transformation. The next topic, item 3, is analyze circuits with dependent sources. Circuit analysis using resistor combinations. So this problem asks us to find all the currents and voltages labeled in the ladder network. If I simplify this portion of the circuit, and I will be able to find the total resistance that I will add there, replace this portion, it will become something like this. And over here we have a 4 in parallel with a 9 plus 3. That's the 12 in parallel with 4. That is how we find the overall resistance, that is 3K. So we replace this network by this 3K resistor, so we get a new simplified network. So this problem seems a little bit easier compared to the previous one to solve for some unknowns from the problem. Because these two problems are equivalent, so this I1 is still the same I1 over there, and this VA is the same as VA over there. This I3 is the same as I3 over there. This VB is basically the voltage between these two nodes. That is the same voltage VB, because we didn't touch these two nodes. We just replaced all the rest who connected to these two nodes by this 3K resistor. So we can do something similar to what we did over there by simplify this part of the network. And we know that this network have a 6K resistor in parallel with another 2 resistors in series. So 6 in parallel with 3 plus 3. That is 3 kilo ohm. So now from your calculation, you also notice that if you have 2 resistors in parallel, they are of the same value, the total resistance will be half of them. So in this case, we have a 6K and another 6K in parallel, so it means the total resistance is 3. So we replace this whole thing between these two nodes by this 3K resistor, and we find the circuit to be very simplified. So we have only 9K and 3K in series, and in this problem we only have I1 and VA. And VB and VC are gone because we did a simplification. But we can solve I1 and VA pretty easily from this network, right? Because in this network we know that there is a 12 voltage applied on these 2 resistors in series. And we already learned that how to find the voltage and current for this voltage division circuit. The VA, we know that is a part of these 12 volts and depends on the ratio of these 2 resistors. So that is a 3 over the total resistance, 9 plus 3 times 12 volts. So that will give us 3 volts. We can also find the current by using Ohm's law, because the current going through over there, by looking at this resistor applying Ohm's law, we can find the current I1 is equal to this 3 volts divided by the 3 kilo ohm. After we find a VA, VA is the voltage between these two nodes. Here we have another voltage division circuit again to find a VB. So VB is part of a VA, depends on the ratio of these 2 resistors. Since they are the same, we know that VB is 3 over the total 3 plus 3, that is half of a VA. So that's how we find a VB. And if we trace it further back, we know VB already is pretty straightforward for us to find a VC. This is the same setup. So the total voltage applied on these 2 resistors in series, that is a VB, 1.5 volts. And the VC that is a part of that, this 3 over the total 3 plus 9 times VB, that is 0.375 volts. So this is how we find out all the voltages. Now from the VC, we can find the current I5 by using Ohm's law. And if we find I5, and we can also find an I4 from VB over here. We know the voltage and we know the resistance by using Ohm's law. We can find I4, and we can do the same thing to find I3 by using KCL. The I3 is the current goes into this node, and I4, I5 are current leaving the node. I3 is equal to I4 plus I5. This is KCL at this node, 0.5 milliamp. And we keep moving, and we can find I2 by using Ohm's law, by looking at this 6K resistor. And we can find I1 by using KCL again. We also mentioned that to find I1, we can also find it from this network by using Ohm's law, VA divided by 3K, that is also 1 milliamp. So we also cross-check the answer. So now we are pretty confident the answer should be correct. So the second topic is delta Y transformation. So we're going to talk about delta Y transformation by using one example. So look at this circuit. We have R1, R2, and R3, and R4, R5, R6. They're connected in this way. So if I ask you what's the connection between R1 and R2, they are not in series, right? At the same time, they are not in parallel because one side is connected to one node, but the other side they are connected to different nodes. So they are not in parallel, and at the same time they are not in series either. If we take another look, we find that R1, R2, and R3 they form this delta-shaped network. If we look at down over here, R4, R3, and R5, they form another delta as well. So in this case, if I want to replace this problem-making section, this delta network, I'm thinking if I convert this delta-shaped network to this Y-shaped network, so this is inverted Y, then the circuit will be something like this. So we keep R4 and R5, replace this delta network by this Y network. And we can see the connection now, right? So RA is in series with the rest, and for the rest, these two branches are in parallel. So we can use whatever we learned from last week to solve this problem now. So then the problem becomes, how do we find the equivalent Y-shaped network? So if we take this delta network out and we assume that these are two the equivalent, so if they're equivalent, it means that if I took a multimeter, I measure the resistance between A and B, it should be the same, the resistance as I measured from here, A and B. If I measure the resistance between A and C, I should get the same answer by measuring the resistance between A and C in the equivalent network. Right? So that is the idea how to find the equivalent network. So let's set up the equations. The first equation tells us that if I measure the resistance between A and B by looking at this network between A and B, I apply the multimeter there. The resistance between A and B, that is simply RA plus RB, because RC is not connected to the network, right? So I just measure the resistance from these two nodes. For the delta-shaped network, if I measure the resistance between A and B, I know that it has two branches in parallel. One branch is R2, the other branches are R1 and R3 in series. This is how I get this result. RAB, that is equal to R2 in parallel with R1 plus R3. So similarly, we find the resistance between node BC and node CA. Now we have three equations. In total, we have three unknowns, RA, RB, and RC. If we find these three unknowns, the problem is solved, right? So by combining them together, I'll be able to solve RA, RB, and RC. In the future, when you see the problem, you don't need to go through the derivation. It's pretty straightforward to about how to memorize the answer. Let's look at that. So RA, the equivalent resistance in the Y-shaped network, RA is equal to R1 times R2 over, this is the total resistance. R1 and R2 are the two resistors connected with node A. So we find RA is the multiplication of two resistors connected to node A divided by the total resistance. And similarly for RB, RB is over here, that is equal to the multiplication of the two resistors connected to node B, R2, R3, divided by the total resistance. And similarly for RC, that is equal to R1 times R3 divided by the total resistance. Let me ask you a special case. What if R1, R2, and R3, they're all the same?
It was 1/3 of R. It was in our quiz.
Yes, you got the answer already, right? So that's how you got it. So that's R squared over 3R. This is why it's 1/3 of R. So the next topic is about circuits with dependent sources. We already deal with problem with independent sources. So now let's look at one problem with dependent sources. Over here, this is the equivalent circuit for FET common source amplifier or BJT common emitter amplifier can be modeled by the circuit down below and determine an expression for the gain of this amplifier, which is the ratio of the output voltage to the input voltage. So the output voltage is over here, VO, and the input voltage is this VI. So we want to find a ratio of VO over VI. We see that there are 3 resistors over here. Simplify the resistor network because we have 3, and you can use this equation to solve that, or you can do like combination of between R3 and R4 first, then you do like in parallel with R5. You can do it in 2 steps, or you do it in 1 step like this. So we can find RL. So we replace this resistor network by a single resistor RL. Then we look at this problem again. So over here we have a dependent source, and this is a current source. This current source depends on another voltage. So this is called a voltage dependent current source. If we just look at the left hand side of the circuit, this is a voltage divider. So VG, that is a part of a VI, depends on the ratio of R2 over the total resistance of these two, R1 plus R2. And on the right hand side, VO is equal to the current times the resistance. And pay attention, this current goes the other way. It's not following the passive sign convention for a resistor. So this is why VO, that is equal to negative current times RL. If you don't like to see that, you define a new current. Say I define a current RL over here, and RL that is equal to negative GM VG. Either way is fine. Now, yes.
What's the unit of GM? I tried to find in textbook, but it was on S. But what is S?
S is a Siemens. This G is a symbol for conductance.
Oh, conductivity. It is conductivity here. GM.
Yes. So it's the inverse of resistance. You don't really need to worry too much about the units, because in circuit analysis, as long as you match the units, this GM times VG, that will match my current. That is fine. So as long as you know that, it's good. You just use it as a current.
Okay, thank you. I got it.
Uh-huh. So now we have VG and we also have VO. We can find the ratio. VO divided by VG, that will give us this expression. So this is the amplification gain.